Welcome. Thank you, everyone, for signing up and coming. I appreciate it. I was shocked that it filled up. My name is Nathan Beyer. I am a senior principal architect, distinguished engineer at Cerner Corporation. Cerner is a healthcare information technology company. We focus on delivering and improving healthcare to various clients throughout the globe. Today, we're going to talk a little bit about population health and what Cerner is doing in that realm. So what you can expect is a quick overview. We're going to kind of jump in so I can give you some background on what Cerner and population health is all about, and then talk about the architecture of the system that Cerner uses for population health. And then we're going to discuss the challenge that kind of led me and my team to Amazon Web Services, and then discuss how we approached overcoming that challenge, as well as some additional learning along the way. So, as I said, to give some background, I wanted to talk a little bit about what population health management is. By a quick kind of raise of hands, does anyone know what I mean by population health management if they say it? Okay, so maybe about 10%. The very kind of high-level definition of that in the healthcare industry would be that it's the coordination of care of a population across care providers and care settings. So what does that really mean? From Cerner's perspective, we've defined a strategy of knowing our population, so knowing who you need to interact with, knowing the set of patients, if you will, although we don't like to use that term too frequently, the people that you are trying to improve the health, engaging with those members of that population and trying to help them engage in that process of increasing their health status, and then providing the providers and organizations that are working with that population and those members to manage those outcomes, to increase the overall health of the population. The way that Cerner goes about doing this is through what we call the Healtheintent Platform, and this is Cerner's platform for population health solutions. The first piece of the platform functionally that we provide is the ability to aggregate and normalize data. And so if you're a little bit familiar with the healthcare industry, you'll know that there's data everywhere. There's not any single canonical place where your data as a person exists. You have data in EMRs at the various hospitals you visit, EMRs in the clinical ambulatory clinics that you go visit. And this data is very messy. It's very dirty. And so we spend an inordinate amount of time trying to clean that up, normalize it, and bring things together. The major goal of that is to create what we call, and what the industry refers to as, a longitudinal record. And this is a record, a person's chart, if you will, that spans all of the time and data that we can get a hold of for an individual within a population. So if you imagine yourself, think about all the places that you've gone to get healthcare from, hospitals, clinics, et cetera, and then being able to see that as a single logical entity. That's the longitudinal record. And so we create this longitudinal record, and then we apply various types of learning and algorithms on top of this so that we can produce, amongst many things, a longitudinal plan. And the point of a longitudinal plan then is to identify how we should be taking care of you longitudinally, not at any one given visit that you might be encountering. So rather than focusing on the care of, say, I have the flu this week, it's focusing on my chronic conditions and my non-chronic conditions as I live my life throughout the years. And then what our system allows you to do then is to be able to act and measure all of these things. And so we'll be able to look at you down to the individual person level so you can engage on your own type of health care, as well as then all of these other roles that will play a part in the healthcare industry. So health coaches, care managers, providers, data scientists, and even healthcare executives. So jumping in and into a much less pretty slide, I apologize. The Healtheintent Platform is made up of a number of components, and this is an extreme simplification of what we've built out over the past 3 or 4 years. This platform is separated into what we refer to as 3 planes. You can think of those as tiers if you'd like. We have a data and processing plane, and in this plane obviously is where we store and process most of the data. So all of that processing pipeline that I kind of implied in the last slide, this all happens within our Hadoop infrastructure. We use Cloudera's distribution of Hadoop, and most of our data is stored using HDFS and HBase. We use both of those for a variety of purposes. There's no single data store. There's lots of data stores that are kind of built out to meet the appropriate needs of processing at each point in our pipeline. We also then have Solr available on our system, and this is both used for sort of natural searching, as you might refer to it, as well as what we generally use this most for is indexing. So index-based searches. If you've ever worked with HBase, you know that it's not exactly the easiest thing to get data out of. You kind of define your question, and HBase can answer a very specific question very well, but it can't answer arbitrary questions very well. So we use Solr to index a lot of the data that we have in HBase, and this provides much better querying services to get at information. And then we have lots of relational databases for very small pieces of what I would refer to as kind of reference data, or data that kind of glues the system together. And then we also use a specialized database called Vertica, and we use this specifically to facilitate business intelligence tools. I won't focus too much on this. We'll talk about it a little bit later. Above this plane of the architecture, we have then what you might define as our services plane. And so effectively, we try to build out a service-oriented architecture at this point in the platform. The goal here being that most, if not all, of the assets that we're building are service-oriented. These services are all internal-facing, and they have a very specific functional purposes. Some people might call these microservices. I don't know that we're micro enough to get into that kind of hip meme there. And then above our services is really then where we start to expose our functionality to end users. And so this is where we build applications and public APIs. And this plane of the architecture only interacts with services. So this has a clear separation of concerns here, where it's intended to be delivering functionality to end users, as well as delivering APIs to consumers. In terms of technology being used in kind of some of these generic places, obviously in our processing tier, we use a lot of Java to do our processing. We use a little bit of Scala here and there. Our services plane is mostly Java-based, and then our application plane is exclusively Ruby on Rails. So the challenge that we ran into, we've had this architecture for 3 or 4 years now, and the issue that we ran into is that, so we've been running this on-premise hosting. Cerner has been running its own data centers for decades now. It's something we're fairly good at. We understand what we're doing, and so on-premise hosting is just the de facto standard. However, in this case, we've run into an issue in that with Healtheintent, we are hosting much more than we've hosted in the past, at least conceptually. as Healtheintent is also trying to bring in a different business model, a more service-oriented business model where we're not providing software off the shelf and then providing you ways to host it as well. We're also providing, we're just kind of boxing it all together and saying this is the service and this is what you get. So we're often looking for ways to constantly reduce our total cost. And so the challenge here really is one around disaster recovery. We initially didn't need a high level of disaster recovery. We have disaster recovery, but it's a very slow process. But we needed to increase that to keep competitive in the market, as well as to just provide a better offering than we had been providing. The core problem there is that we didn't just want twice the compute capacity in our on our capital spending. So we started looking at other opportunities. In addition to that, we obviously are very concerned about the security of the system, specifically the security of the data. We obviously deal with a lot of PHI or protected healthcare data. And so we have a lot of security controls that we have to meet both from our external regulatory needs as well as just our internal level of controls. And so we have to meet, obviously, HIPAA and high trust. We run controls up to meet the NIST 853, as well as then all of the various controls that we've decided we want to go meet. And so these are kind of the two major pieces that we needed to achieve. And this kind of led us down the path to a variety of public cloud vendors. And specifically, this led us most directly to AWS. The reason that this kind of led us to AWS is that we defined a very simple approach for what we kind of refer to as on-demand disaster recovery. And this design is we tried to keep it extremely simple, and that what we really wanted to do was just provide a mechanism for replicating all of our raw data. And when I say raw data, this is all the data that's kind of being pushed into our system, the dirty, unclean data. We can recreate any of our processing states by just reprocessing the system. We're fairly good at that. We built the platform from day one to be able to reprocess everything from scratch. And so what we wanted and what we needed at a minimum was just an ability to move data from our local on-premises data stores, replicate that somewhere in the cloud, and then potentially we would also like to replicate intermediate data, not because we needed it, but because this provides us a mechanism of recovering faster. So even though we can reprocess everything, that doesn't necessarily mean you want to, because you're talking days and weeks of processing for clients. And so that simple process is that we wanted to replicate our raw data, move that over to, in this case, we start replicating it to S3, and then in the case of a disaster, we would spin up another data store replication of what's on premises, and this is HDFS. And then we would also spin up the various types of data stores for our intermediate data. This is HBase, MySQL, et cetera. And then spin up all of the compute needs to recreate all of the processing, recreate all of the application services, et cetera, and then just start switching users over. Clean and simple like that, right? Nothing too complicated. Obviously, this isn't a simple challenge. If any of you have ever tried to do hybrid clouds and tried to do disaster recovery, there are lots of details for which the devil can appear. Also, because this is what I suppose you would refer to as a big data platform, we are talking about petabytes of data. So we currently have around 100, growing more on a daily basis, 100 clients, and that's maxing out our local data stores, it's somewhere around 5.6 petabytes of data. We won't be replicating all 5.6 petabytes of that data instantly. Beyond the difficulty of just moving that data over, we also have the difficulty of you have to convince clients that they do want to participate in this. And this is an interesting challenge within the healthcare industry in that if you are in the healthcare industry related to technology, you know that everything related to being the edge of high tech in healthcare is about 20 years behind. And so this isn't necessarily a statement on how the technology is there or not, but it is a statement on how slowly things move throughout the industry. There is an enormous amount of regulatory concerns, enormous amount of security concerns, and just in general, lots of fear and uncertainty. And so things move very slowly. And so we have to take into consideration that we can't just flip a switch and all of our clients are okay with us moving data to Amazon Web Services. This is our goal, but we have to be able to do this kind of one at a time. And at that level, we're talking about terabytes of data, and then on a daily basis, replicating gigabytes of data to keep up with things. So the way that we started off this process is setting up data replication. So this is obviously the first core piece of that disaster recovery mechanism. So we have to both bootstrap that data, start it from a point in time from which we can then start replicating that information, and then we also have to get the replication running. So to do that, the way we chose to go about doing that, to make sure that we were in compliance with HIPAA, various security controls, and our own security controls, what we decided to do was take the raw data, run it through an encryption, and encrypt all of it using client-side encryption, if you will. And we encrypted it in our data center on premises. This is obviously just a MapReduce job that we ran. We just ran encryption, encrypted all the files. And then we dropped that encrypted data onto a Snowball device. So the Snowball devices are HIPAA compliant as part of Amazon's HIPAA compliancy. And so part of working with AWS, if you do have to deal with PHI, is making sure you're HIPAA compliant. And then in the US, what that means is that you work with Amazon to sign a BAA, if you're familiar with that concept, a Business Associates Agreement. And part of that agreement is that as a consumer of the Amazon Web Services, you have responsibilities in maintaining the various security controls. And as I mentioned, so we decided to do our own encryption. This is not the only way to do that. You can use the built-in encryption mechanisms that are and have been available with Snowball to do Snowball and S3-based encryption. We chose to do it this way, and so obviously we drop it on the Snowball, ship the Snowball out. A few days later, that shows up in a new S3 bucket, all encrypted. We spin up Hadoop quickly, take our local encryption keys, decrypt that data, and then now we have that bootstrap state of our replicated raw. We don't intend to do this frequently. We're hoping to do this only a few times, but as I said, it kind of depends on as clients agree to this and move across to this. But it is a fairly straightforward process and one that seems to work pretty well. Obviously then, after we've got that data bootstrapped, we flip the switch and that ongoing replication happens. The way that this works for us is that in our architecture, so I didn't detail this out, but we utilize Kafka within our ingestion services. And part of that allows us kind of a very nice feature is that we can publish incoming data from queues that come in the Kafka topics. And we're always taking those topics and storing that data historically forever. But for this replication, what we can do is we can kind of bifurcate, or in reality, it's just spinning off another publication of those queues. We have much more than just 2 pieces of that, but we just spin off another piece that just captures that data and sends it directly to S3 with very little code change on our part. Most of that was really setting up a lot of networking, because another part of that BAA that you have to sign in to keep HIPAA compliancy is that all of the PHI that you are sending has to be sent over a encrypted transport. So part of that is then, as we're publishing that data from our Kafka queues to S3, is to make sure that that's going over a TLS-based encryption transport. Okay, so once we have the data set up, the next big piece for recovering and restoring is actually laying out the network and kind of the arena where things will go. So obviously, our goal here was to not build out everything. We wanted to build out just enough of an infrastructure, and we'll keep some of that infrastructure running all the time. And most of that infrastructure that's running all the time is intended to be just what keeps the lights on. But what we had to build out is a kind of a peer to our local networks. And to do that, so I tried to lay out this diagram where we've got, on the right side of the diagram here is kind of some of our on-premises components, and then the AWS structures that we're going to look through here. And so one of the first things that we need to work out was how are we going to allow operators and any identity in the system to interact with AWS componentry through using our specified security controls. And to do this, we decided to use AWS's IAM and federate that using Active Directory Federation Services. So that piece that says ADFS STS, that's Active Directory Federation Services Simple Token Exchange Service, I believe. But this is the federation service. It's using SAML, et cetera, to communicate back and forth with IAM. Part of our security controls is that we use 2-factor authentication, so we have username and password, as you might expect. And then we also have a second factor of authentication, which is using RSA secure tokens. And that is all implemented behind ADFS, and then IAM just understands all of that and is configured to challenge using multiple factors. The next step then is setting up the arena for where we'll be running the system. And so what we've had to set up is 2 VPCs within what you might call kind of our production arena. There's a production part, which is where all of the actual components of the system as it's running and when it gets recovered will be running. And then there's a management VPC. And this is a part of the system that has to be running continually in case you need to do that recovery operation. We're running these components all the time, and this keeps everything up and going. And so the way that these are kind of laid out is that each of these VPCs is isolated from each other, and then they have a gateway that allows the management and the production to communicate back and forth through a securely controlled channel. And this, we've got various security policies using the various pieces of AWS networking. And then each of these needs to communicate back to our on-premises network. And on-premises, then, we create these virtual private gateways for both of those VPCs, and they connect back through our firewall. And so this part of the system will always be running. This will be continually up and moving. And as kind of a quick side comment, so the intent of all of this is to have a disaster recovery mechanism. Obviously, parts of this architecture might look like they're singletons, but our on-premises systems, so our on-premises infrastructure, such as these firewalls, ADFS, et cetera, they all have their own on-premises form of disaster recovery, and they are a separated concern. So if there is a disaster in those cases, those things have their built-in on-premises failover, so we're relying on top of that to make sure that these components can always be running. So then, within this, once we want to establish the system and kick things off, we need access to our code. We need access to all of our configuration management artifacts and our code to get things running. And all of these components are running on premises. We utilize GitHub Enterprise for all of our source code management to store and do Git operations, basically. And then we use the Nexus artifact repository to store all kinds of things. So basically, it's our Maven repo, our Chef Supermarket, Ruby gems, et cetera. All of these things are dropped into there. And once we have access to that componentry, then we can connect things up, and then that allows us to kind of build out the system, which I'll talk about in some oncoming slides. But effectively, then we lay out that production component with a bunch of isolated networking tiers such that our data is separated from our applications and our services, and then those are separated from the load balancers and so on. So this gives us then a fairly simple system to reason about, as well as a very secure system for us to operate and manage. If any of you have looked at some of the various AWS white papers around the NIST 800 security, some of this might look a little familiar. So we borrowed some of these constructs of having a management VPC from your production VPC from there. And so that's where this Bastion EC2 instance comes from. And so a Bastion instance is the mechanism for connecting into the production system. I didn't lay out a bunch of directional arrows here because it made things a little too complicated, but effectively, you can only get into, an operator can only get into the production nodes if they go through the Bastion node. So you have to SSH through the Bastion node and then through to all of those instances. That virtual private gateway that connects back to the firewall is really only a one-way connection. There's no connections back, especially for operator purposes. So everything that comes in through there goes in that pathway. And then Rundeck, I'll talk a little bit about this, but this is for orchestrating and part of our deployment mechanisms. All right, so this gives us kind of the layout and kind of the arena to work within. From there, then, we needed to build out our orchestration design and to figure out how we were going to automate and get all of these things kind of running and spun up from soup to nuts. And so what we looked for is we wanted to do a few things. We wanted to try to use as much of the existing componentry that we have on premises, and we wanted to utilize as much of the native AWS services we could get to. And so we kind of tried to get to a nice balance here of things that we use on premises and then things that we're going to continue using in AWS. And so on premises, we've been using Chef for a very long time. Chef is our infrastructure automation and allows us to do the deployment and setup of all of our components. We've been experimenting with Rundeck on premises for the past year or so, and we found that that was a fairly useful component. We hadn't completely adopted it on premises, but we thought that it would work very well within this context, so we started using Rundeck within this context. But the difference here being that we started interacting with AWS's CloudFormation templates and automation to try to facilitate the most natural and native use of instantiating EC2 instances, instantiating RDS, setting up your VPCs, et cetera. We found that that kind of combination of things worked best for us. So we adopted CloudFormation and kind of tied that together with Rundeck. And then that all ties back together with Chef, which is what gets run individually on instances. If you're not familiar with Chef, the way Chef really works is that you define recipes that you're going to run on an individual instance, and then those recipes execute a bunch of steps and set up that node. Well, the way that that works is that you kind of have to tell the instance to go set itself up in that fashion. So Chef has to be run on every single node. And we facilitate that through getting CloudFormation to kind of set up base images or instantiate instances off of base images, and that part of that base image then bootstraps with connecting to the Chef server and then spinning up and running various recipes. And as I mentioned, so we have to connect back to our internal GitHub and our internal Nexus repository to pull down lots of things. So those things that get pulled down are obviously our source code in the cases of where it is. So with Chef, there's no compiled end state, so you kind of just get the source code directly from everything else that is actually compiled and packaged. You can pull that directly from Nexus, and Chef will facilitate doing all of that. So these are just the components that we went with and we kind of started playing with, and kind of this was the toy box that we gave to the team. And so what they ended up with then is building out an orchestration flow that kind of looks like this. If we were to flip the switch, and I'm trying to correct my tenses here, we do this frequently, so we actually execute these switch flips all the time. And so when we do flip the switch, what we're doing is instructing Rundeck to kind of kick things off and start restoring the system, or also we can just say build the system. It's not necessarily limited to restoration. What that is Rundeck interacts with CloudFormation, and the very first thing that Rundeck's going to do is tell CloudFormation to start setting up components of our Hadoop infrastructure. The first component that it sets up is Oozie, and if you're not familiar with Oozie is Hadoop's form of job orchestration. So we run all of our jobs through Oozie. So Oozie is kind of that command center. So the first thing it needs to get set up is Oozie, and then we finish setting up Hadoop. So we set up the HDFS services, the HBase services, as well as spawn off and set up a complete resource network. And so in this case, we're talking about in our tests, we're only doing like 10 to 50 node Hadoop clusters. But as we're scaling up our tests and scaling up the number of clients, you're getting closer to hundreds of, and we'll top out at about 1,000 node Hadoop cluster. So once Hadoop is set up and running, we start setting up a few other things, some of our operational services, and then Oozie will be instructed to start kicking off some of these core jobs. So kicking off kind of those core processing jobs. The first thing that it needs to do then is pull all of that information from S3. So this would be that replicated raw data. We need to pull that back in and start processing and cleaning up that information and creating those longitudinal records. Once that gets to a functional state, we start to there's a lot going on inside those processing jobs. So we're talking about, we've got hundreds of jobs that kind of run and do lots of processing and in sequence. We start to get to a point where we move that data out to our other functional services, one of those being Vertica. So we have to set up that Vertica cluster. Vertica runs in, we've got clusters. We run this in groups of clusters. So we run about a cluster of 11, that's 10 plus 1, the way that they suggested. And then we run about three of those for, say, 40 clients or so. This will start pushing data into Vertica. And then at this point, we can start setting up and instantiating our application service components. Those components will be connected to HBase and Solar. And so this is because data has started to manifest in HBase and started to populate. And then at that point, we start to set up our applications. And so this is obviously spawning off a number of EC2 instances. And then those all get connected up to the services. So there's no actual connection there, but these connect up. And then all of these things start running all of their various health checks, our monitoring processes, start watching the system, and start checking to make sure that everything's running, that we get a bunch of green lights. And then at this point, then we can flip over DNS and start moving traffic over to these application services. Now, obviously, our challenge and our focus was to try to work on this for disaster recovery on demand. But the way that we approached this was essentially we just wanted to run Healtheintent Platform in AWS. And so the way that this kind of landed, even though we have a little bit of facilitation of restoring the system, restoring some of that raw data, there's really nothing unique about this that limits it to disaster recovery. And so we utilize this system for a number of development purposes, but we're also considering utilizing this in the coming year for new market entry and spawning up new regions for our market. So we're looking at, can we use the Canada and Australia marketplaces by using AWS exclusively. So rather than having on-premises with disaster recovery, for those regions, we're looking at we'll have just everything running in Amazon Web Services. And that will require no change to all of this investment that we've put together here. And so that's kind of a nice side effect value that we've gotten out of this entire project. So to kind of talk about where we are now, what we have at the moment is we have 2 of our clients who, live and ready, and so they are capable if there is a disaster of some scale. And so this is really kind of up to us to determine what that disaster is, if it's a small disaster or if it's a whole data center being taken out kind of thing. We can then flip them over. Currently, we're looking at, we have a 12-hour recovery time, so it takes about 12 hours from saying we're going to recover to actually having the full functionality. So there's mixed functionality in there that as this is a fairly decoupled system, there are many components that can be running and value that can be gained out of the system, but not everything is 100% running. So we can have some parts of the applications can be utilized much earlier in the recovery than other parts. So some of our business intelligence tools they do a lot more processing, so there's a lot more time for those to go on. We're continually working on trying to get that time down. One of the things that we're focusing on is spending time doing intermediate recovery and trying to find some of the best places where we can do intermediate data store replication, where it's not too expensive for us to replicate that data and kind of maintain that data replication, such that we can do a recovery that takes only an hour or 2, and we have a functioning system, but it might be degraded, so the data may not be, it may be an hour or 2 hours behind. And so you get the system up and running, and then the users of the system, they see slightly old data, and then the full processing catches up with them at some point. And so, and then within that recovery period, they get full recovery. A lot of the focus that we're working on, so a big challenge is just getting all of this running. So for anyone who's actually using AWS today, right, and for any purpose, small or big, there's always just a lot of testing and a lot of a lot of little edge cases that kind of pop up all the time. And we're constantly running into those. Some of those are just, we didn't read the manual very well. Some of those are, we've got code that's just not behaving as awesomely as we thought it was. Our automation isn't very resilient. I've personally found that I think we need to spend some time on trying to think about resiliency a little more. The resiliency of our automation, especially, is a little difficult. We've kind of sat on our laurels in some cases where we've relied on humans to do things that really isn't acceptable and really degrades the recovery time. And so we're spending time on trying to tighten up that automation and make it much more resilient. And doing this is so that we're constantly running tests and doing things like that, but we're also doing drills, or what I think we've borrowed the term game day exercises, where we actually do a disaster scenario. For us, those kind of game day exercises, not only is it just a good idea, but we actually have requirements to do those things. So, we have various contracts that have kind of forced us to do that, as well as regulations that have kind of forced us to do that. But it's a great thing to do, and something that I highly suggest is that always test the resiliency of your system, especially if you're saying you're offering a disaster recovery solution. You need to actually test that disaster recovery and force it out and see what you can do. It helps kind of find lots of latent issues and lots of latent bugs. So on our journey, we did find a few other value propositions in using AWS. One of the more interesting ones that we've been trying is we've over the past year that we've been working on this DR on demand project, we also kind of concurrently had this idea that we've been wanting to get better at our operational management of the system and understanding how the system's being used. We have plenty of information and metrics in our system, so lots of data is there, but we weren't necessarily harnessing it and using it. And so we kind of came up with this obvious idea that was, well, we need to get it into a warehouse. We need to pull it together and do what you do with data warehouses, like get it together, clean it up a little bit, and then start using it and start creating, daily operational reports and see what's going on and try to get functional insights into our system. And so as we were working on the DR on demand project, we wanted to kick off trying to do this. And so we found that as we were trying to build out some of this automation, that there was some interesting simplicity in using some of these services that AWS offers. And so we decided to try using those services to build out this operational data warehouse. And we built out this very simple data warehouse and ETL pipeline, which is effectively we just push lots of data into S3 in a very raw form as we can. And then we write little AWS Lambda scripts that get launched off based on S3 events. And so we found that Lambda and S3 and that eventing infrastructure kind of creates a very low friction ETL pipeline. Obviously, I don't know how far this will last us, but what it allowed us to do is build a very quick ETL pipeline, do it with trivial amounts of code. We're talking like dozens of lines of code that you go write a little Lambda function, throw it out there, get it connected, and start inserting data. We decided to test out Redshift because we wanted to see what that was all about. We liked that Redshift offered kind of a Postgres compatible API, as well as we were curious to see just what it could do in terms of evaluating Redshift, also in comparison to some of the other technologies that we use for our own analytical purposes. And so we kind of connected these things all together, and so now we have this operating data warehouse that, although it's certainly not the most robust and fancy data warehouse mechanism ever built, what it is it's extremely simple for something that does not get any focus. Right? So if for any of you that are in engineering teams who are constantly being asked to build more functionality, building a operational data warehouse that only helps you isn't really something that you're going to get buy off from your product managers or solution managers, whatever you call it. And so this is easy for us to kind of just do and make it work, and then prove the value proposition of it. And then if it needs to expand later, we can. So I would highly recommend, if you haven't played around with AWS Lambda and this kind of serverless construct, there's a lot of little interesting pieces that I think it fulfills. I think there's a huge future there for the serverless marketplace, and I'm not quite sure where that will land, but I do think it provides enormous value right now for lots of little bits of kind of that DevOps automation and gluing together a few little things just to keep things running. We found it to be really interesting, and looking at a bunch of other kind of little bits and pieces that we can tie together with Lambda. A lot of the engineers are super excited about it. They're just, it's also something really cool to get used. We have not gotten to use QuickSight yet. I hear it's really cool. We haven't quite jumped on that. If anybody knows about that, I'd love to hear your experiences on that. We're kind of interested in that. We're a Tableau shop, so we do a lot of Tableau usage on our analytics data warehouses. That is everything I have today. If you have questions, I'll be around for indefinite period of time, so feel free to talk to me. I didn't want to go too much over because the next session is coming quickly. I appreciate everyone coming out and everyone staying. Thank you very much. Have a good session.